Somewhere in the darkness of space, a dead star turns with perfect rhythm. It no longer shines like an ordinary star, yet it sends out a steady pulse that can cross the galaxy. These strange objects are called pulsars, and they are among the most extreme and mysterious things ever discovered. Before the journey begins, thank you for watching and for supporting the channel with every like, subscribe, and share. It always means a great deal. It would also be wonderful to hear what time it is and where in the world this video is being heard tonight. Now, let us gently begin the story of pulsars. In the ordinary view of the night sky, the stars seem patient and almost unchanged. They rise, drift, and set with a calm that suggests permanence, even when their light trembles above Earth. The cause usually lies close at hand in the moving air, not in the stars themselves. For most of human history, that impression remains strong. The sky appears full of distant fires that burn with great violence, and yet present themselves as steady points. Then astronomy begins to look beyond visible light, and the old stillness starts to loosen. Radio telescopes spread across fields, and hillsides begin listening to the sky instead of simply watching it. They do not search for shimmer or colour, they search for rhythm. In the late 1960s, that search reveals something the eye could never have found. Amid the background hiss of the universe, certain sources flash with astonishing regularity. They brighten, fade, and return again with such precision that the signal seems at first almost artificial. The intervals are so exact that the first reaction is caution. A natural object is expected to drift a little, to blur, to wander. These signals do not behave that way. They arrive on time, again and again, with a steadiness that feels nearly mechanical. The sky, which had seemed vast and uneven, suddenly contains something that acts like a perfect clock. This is where the mystery of pulsars begins, not with an image, but with a beat. The earliest detections come from radio observations, where the sky appears very different from the one known to the eye. Invisible structures glow, fade, and spread across darkness in patterns that do not match the stars seen at night. In that hidden sky, a young researcher named Jocelyn Bell Burnell helps identify a source whose pulses repeat every little more than 1 second. The signal is so regular that it stands apart from all the usual signs of interference. It does not come from nearby machinery. It does not match aircraft, satellites, or known terrestrial noise. It comes from deep space. For a brief moment, the possibility of intelligence enters the edges of the story, not because the evidence supports such a conclusion, but because the precision feels difficult to absorb. That idea soon recedes as more of these objects are found. The sky is not holding a single strange beacon. It is holding a whole class of them. Once several are known, the interpretation changes from unlikely message to unknown star. The regular pulse remains, but the source becomes part of nature again, though of a nature far stranger than expected. The name pulsar emerges from that behaviour. It is a star that seems to pulse, yet even this simple name hides a deeper truth. The object itself does not swell and shrink in the way the word might suggest. In most cases, the beam of radiation sweeps through space, and Earth happens to pass through its path again and again. The pulse is not a heartbeat in the usual sense. It is a lighthouse effect. A rotating source throws narrow beams into the dark, and when one of them crosses the line between the star and Earth, the telescopes register a flash. This explanation sounds almost simple once stated, but it opens a far more unsettling picture. For such a beam to flash so rapidly and so precisely, the source must be small, dense, and rotating at extraordinary speed. An ordinary star does not behave this way. A red giant cannot turn many times each second. A broad sphere of hot gas would tear itself apart. Something much more compact must lie at the centre of the signal. From the start, the pulse carries a hidden implication. Whatever produces it belongs to a class of objects formed under extreme pressure, beyond the everyday life of stars. In time, astronomers connect pulsars to neutron stars, the collapse remnants left behind when massive stars die. This connection makes sense of the timing, the energy, and the narrow beams. It also transforms the emotional shape of the discovery. The pulsing points in the radio sky are not merely unusual stars. They are stellar remains, dense corpses of once brilliant suns, rotating in darkness long after the main light of the parent star has vanished. The signal from a pulsar is therefore both present action and ancient aftermath. It is a remnant speaking in intervals. The known facts already feel severe. A neutron star forms when a star much more massive than the Sun exhausts its fuel and can no longer support itself against gravity. Its core collapses, its outer layers are thrown into space. What remains is a body only about the size of a city and yet heavier than the Sun. In some cases, this remnant rotates with immense speed and carries a magnetic field of almost unimaginable strength. These are not decorative details around the signal. They are the only conditions that make the signal possible. The pulse in the radio data becomes, on closer examination, a sign of a place where matter has been forced into one of the most extreme forms known in the universe. Even before the inner structure of such an object is discussed, the outer behavior alone produces unease. It is one thing for the universe to contain explosions, collisions, and heat. It is another for it to contain an object that keeps time with such cold precision while holding the wreckage of a dead star inside itself. The strangeness deepens as more pulses are catalogued. Some pulse slowly, taking seconds between flashes. Others race far faster. A few eventually prove to spin hundreds of times in a single second. That range hints at different histories and different environments, but it also suggests that the simple image of a flashing beacon is not enough. Pulsars are not one tidy group. They are a family of extremes. Some live alone. Some orbit companion stars. Some seem ancient and worn down. Others remain young and energetic, still embedded in the glowing debris of the supernova that created them. The Crab pulsar, found in the remnant of the supernova seen from Earth in the year 1054, becomes one of the clearest examples. It flashes across multiple wavelengths and confirms that these objects are not radio curiosities, but broader engines of high-energy emission. A point in space that once seemed like a faint irregularity in a graph now stands revealed as a rotating remnant inside an expanding cloud, left by a star that died nearly 1,000 years ago. The scale of that chain is hard to settle into. A brief flicker in a telescope trace leads outward to a historic supernova and inward to crushed matter. Yet certainty does not fully replace mystery. The first explanation solves only the first layer. A neutron star can account for the rapid timing, but not every detail becomes clear at once. Why do some beams remain stable for years while others drift or vanish? Why do some pulsars slow smoothly while others suddenly jolt in speed? Why do certain neutron stars emit strong radio pulses, while others speak in X-rays or gamma rays, or fall quiet altogether? Even at the beginning of the subject, the pattern is already familiar. One fact settles into place and reveals two more that do not. The universe does not offer the pulsar as a neat answer. It offers it as a controlled signal from an uncontrolled past. In that sense, the discovery changes the sky twice. First, it shows that hidden wavelengths contain their own landscape, rich with structures no human eye can directly see. Then it reveals that among those hidden sources are objects so compressed, so magnetized, and so exact in their rotation that they seem to stand slightly outside ordinary experience. The night sky still appears calm above Earth. The stars still seem fixed. But behind that stillness, certain dead stars continue to turn, each rotation sending a blade of radiation through space. Most of those blades never cross Earth at all. A great number of neutron stars likely remain invisible because their beams miss the planet entirely. The pulsars that are seen may therefore represent only a fraction of a much larger hidden population. This possibility adds a final quiet tension to the opening of the story. The observed pulses are not the whole phenomenon. They're only the cases in which geometry briefly aligns. The sky may be full of these remnants, spinning in silence from Earth's point of view, announcing themselves in directions no human receiver occupies. What appears rare may be common. What appears precise may emerge from violence. What appears to blink may, in truth, only sweep past for an instant before vanishing back into the dark. Long before a pulsar begins to sweep its signal across the dark, its story unfolds inside a far more ordinary star, though ordinary only by cosmic standards. The star starts as a great sphere of gas gathered from a cold cloud, and for millions of years its own weight presses inward until the centre grows hot enough for fusion to begin. Hydrogen atoms join and become helium, and that joining releases energy. The outward pressure from this energy balances the inward pull of gravity, and a long, stable phase begins. In such a state, the star seems almost self-contained, a bright object holding itself together through an equilibrium so exact that any distant observer might imagine it could continue forever. Yet this balance depends on fuel, and fuel does not last. For a star far more massive than the Sun, the process unfolds faster and more violently. The greater mass drives stronger pressure into the core. The stronger pressure raises the temperature. The higher temperature consumes the fuel at a much greater rate. A heavy star lives with intensity and dies before lighter stars have reached middle age. During its active life, the core changes in layers. Hydrogen gives way to helium. Helium can in turn fuse into heavier elements, and then heavier ones still. Carbon, oxygen, neon, silicon. Each stage grows shorter than the one before it. What once lasts millions of years begins to last thousands, then years, then days. The star becomes a furnace that must burn ever hotter to resist its own gravity. In its final stage, the centre fills with iron. That moment carries a special weight in stellar physics, because iron does not release energy when fused into heavier nuclei under the conditions found in the core of such a star. The chain that has supported the star for its entire life reaches a dead end. The light still streams outward from the surface for a brief while, and from far away the star may look unchanged. But deep inside, the structure has already begun to fail. Gravity has been waiting through every stage of the star's life. It never weakens. It never pauses. It is held back only by the pressure generated in the core. When that pressure falls away, the change is immediate. The inner regions of the star begin to collapse. The speed of this collapse is difficult to picture because it moves far beyond ordinary experience. A mass greater than the Sun begins to fall inward in less time than it takes to complete a single calm breath. The core shrinks, density rises, and temperature surges into the billions of degrees. Electrons and protons are pushed together under the immense compression and combine to form neutrons. Neutrinos pour outward in staggering numbers. Matter changes its character in the span of moments. What had been a normal stellar core becomes a compressed region where the usual arrangement of atoms can no longer survive. For a short interval, the collapse races ahead almost unchecked. The core falls inward until neutron pressure and the resistance built into quantum rules begin to halt the descent. The inward fall does not continue forever, At a certain threshold, the core becomes so compact that it stiffens abruptly. Infalling matter from above crashes into this dense interior and rebounds. A shock forms. Neutrinos, released in overwhelming abundance, stream outward and help drive the violence. The outer layers of the star are blasted into space. The star explodes as a supernova. This event is often described in simple terms as an explosion, but the reality is more layered. Part of the star is not blown apart at random. Part of it collapses, hardens, and remains. The supernova is therefore two things at once. It is a destruction and a revelation. The bright outer star is torn away, and the hidden core stands exposed as something entirely new. This remnant is the beginning of the neutron star. If conditions are right, it may also be the beginning of a pulsar. Seen from a distance, a supernova is one of the brightest events in the galaxy. For days or weeks it can rival the light of billions of stars. Ancient observers noticed such outbursts as new stars appearing where none had been seen before. The remnant of the explosion then expands for centuries, sending gas and dust outward in widening shells. The Crab Nebula is among the most famous examples, a cloud still spreading through space after the death of a massive star witnessed from Earth in the 11th century. At its centre lies the compact remnant, and that remnant pulses. The visible cloud and the invisible timing source belong to the same event. One shows the violence spread outward, the other preserves the violence compressed inward. This connection is part of what makes pulsars feel so strange. The signal detected in a radio dish is not merely a present action. It is the disciplined motion of matter that has survived catastrophe in an altered state. The newly formed neutron star is small, but not in any trivial sense. A star that once stretched across millions of kilometers leaves behind a body only a few tens of kilometers across. Mass that once occupies a vast sphere is packed into a space comparable to a city. The compression is so extreme that analogies become awkward. A mountain placed on Earth remains a mountain. A mountain placed into a neutron star scale would no longer resemble itself at all. The language of everyday objects strains under the density involved. A spoonful of neutron star matter, if it could somehow be removed and survive elsewhere, would weigh more than any ordinary structure could support. Yet even this image stays incomplete, because the matter does not simply become heavier in the usual sense. It enters a state shaped by forces that rarely dominate the visible universe. The atomic structure collapses. The distinction between separate particles becomes less intuitive. Matter is no longer arranged in the gentle way it is in rock, water, or air. It becomes compacted almost to the limits allowed before complete gravitational collapse would carry it further into a black hole. There is another transformation happening during this collapse, one that becomes essential later. As the original stellar core shrinks, its rotation speeds up. This follows the same broad principle seen when a spinning skater pulls in the arms and turns faster. Though in a neutron star the scale is incomparably greater, a slowly rotating core can become a remnant spinning many times each second. At the same time, the star's magnetic field is compressed and intensified. The field lines are dragged inward as the core contracts, and their strength grows enormously. Rotation and magnetism become locked together in a new geometry. If the magnetic axis is not perfectly aligned with the spin axis, the remnant may send beams of radiation into space as it turns. Under those conditions, the neutron star is no longer just a collapsed core. It becomes a lighthouse of the aftermath, even before that beam is considered. The formation itself contains a quiet mystery. Not every massive star leaves the same kind of remnant. Some cores collapse so completely that no neutron star remains, and a black hole forms instead. Some explosions may fail in part, with the outer layers falling back inward after the initial blast. Some remnants acquire companions, feeding on nearby matter and changing their later lives. Some are born spinning rapidly, others appear slower. The dividing lines are not perfectly simple. Mass matters, but so do rotation, composition, magnetic history, and the details of the collapse. Astronomers can model much of this process with increasing sophistication, yet the final moments of a heavy star still resist full clarity. In simulations, shocks can stall. Neutrino heating can revive them or fail to do so. Turbulence, asymmetry, and instabilities influence whether the dying star sheds its outer layers cleanly or struggles through a more chaotic transition. The textbook picture remains broadly true, but the real event is probably less symmetrical and less tidy. The star may lurch into death rather than pass through it smoothly. In some cases, the newborn neutron star may even be kicked across space by asymmetries in the explosion, launched at tremendous speed as if the violence itself cannot remain evenly balanced. That possibility adds another subtle disturbance to the formation story. The remnant does not merely survive the explosion, it may be thrown from it like a dense seed from a shattered shell. This invites a wider speculation grounded in the evidence. If the final collapse of a massive star is as sensitive as models suggest, then each pulsar may preserve not just the fact of stellar death, but the signature of how that particular death unfolded. Its spin, magnetic field, speed through space, and later emissions may all carry traces of the last seconds of the parent star. The pulsar then becomes more than a remnant. It becomes a compressed record of collapse, a physical memory sealed into a rotating sphere of neutrons. Much of that memory remains difficult to read. Observers see the pulses, estimate the field, track the slowing rotation, and sometimes locate the surrounding debris. Yet the exact chain from living star to neutron star is never fully visible in real time. By the time the remnant is studied, the main event is already over. What remains is aftermath, precision, and inference. A bright star lives fast, reaches iron, collapses, explodes, and leaves behind one of the strangest objects known. The broad path is clear, the exact inner passage is still partly hidden. It is in that hidden passage, between the stable burning star and the compact flashing remnant, that the familiar order of stellar life gives way to something colder, smaller, and far more difficult to understand. Once the remnant forms and the outward flash of the supernova begins to fade, the neutron star remains behind as a small and concentrated fact, almost absurdly compact against the scale of the event that created it. The parent star may once have stretched across a distance larger than the orbit of inner planets. Yet the object now left at the centre is only about the width of a city. Its diameter is measured not in millions of kilometres, but in a few tens of kilometres. That contrast does not merely sound dramatic, it changes the physical meaning of the object. A star is usually understood as a broad sphere of hot plasma, diffuse by comparison with a planet, held up by pressure from fusion in its core. A neutron star is something else. Fusion no longer supports it. Most of its interior is no longer arranged as ordinary atoms. Its bulk is held in a narrow space where gravity has pushed matter to one of its harshest known limits without carrying it all the way into a black hole. The mass of the Sun, or more than the Sun, is gathered into a body so small that ordinary intuition has little room to operate. Density becomes the first unsettling feature. Descriptions often compare neutron stars to mountains compressed into grains or to planets squeezed into rooms. But such comparisons are only aids for the mind. They do not truly reproduce the scale of the compression. Inside this remnant, matter is packed so tightly that empty space, which usually makes up most of the volume of atoms, is largely erased. The familiar architecture of matter is dismantled. Electrons no longer orbiting atomic nuclei in the ordinary way. In much of the interior, the distinction between one nucleus and the next begins to break down. The result is a substance that cannot be held or touched in any normal sense, and that cannot remain itself outside the star that confines it. This means the neutron star is not just dense matter located somewhere in the galaxy. It is dense matter made possible only by the star's own crushing gravity. The object and its state are inseparable. Remove the gravity, and the matter would not remain as it is. This already creates a strange inversion. Most objects are defined first by their material, and only then by their shape or environment. A neutron star is defined equally by the field that traps it. It is matter under sentence, compressed into obedience by gravity. Heat adds another layer. Although a neutron star is the remnant of a dead star, it is not cold in any human sense. At birth, its interior is searing, with temperatures rising into the billions of degrees. Even after cooling for long stretches of time, the surface can remain at hundreds of thousands or even millions of degrees depending on age and activity. Yet this heat does not spread the star outward the way heat does in a living star. It remains confined. The surface can glow in X-rays, but the body itself stays compact, held down by a gravity so intense that thermal pressure alone has little hope of changing the shape. This is part of what makes the neutron star feel unnerving. Heat is present, but it cannot soften the structure. The object is both furnace and prison. Its glow suggests activity, but its compactness suggests restraint. The two conditions exist together without easing each other. Gravity on the surface reaches a severity that borders on the abstract. A person standing there in imagination does not really stand at all. The difference in gravitational pull between head and feet across the length of a human body would be catastrophic. Tidal forces, meaning differences in gravity over small distances, become immense because the mass is concentrated into such a tiny sphere. The effect commonly described as spaghettification does not belong only to black holes. On a neutron star, too, the lower part of an extended object would be pulled much more strongly than the upper part. No material familiar on Earth could resist such stress. This makes the surface of a neutron star less like solid ground, and more like a boundary where ordinary structure loses its privilege. Even light does not leave untouched. The star's gravity bends the path of light passing nearby, curving the apparent geometry of the surface. An observer far away can see more than half of the star at once, because light from the far side is deflected around the compact mass. The remnant behaves, in this limited but real sense, like a lens shaped by gravity. It changes not only the fate of matter, but the route by which the star is seen. Time is altered as well. General relativity predicts that clocks run more slowly in stronger gravitational fields. Near a neutron star, this effect is no small correction. Processes at the surface appear slowed relative to those farther away. The star therefore exists not only in an extreme place, but in an extreme rate. Matter, light, and time all pass under a different rule there, though the rule is still part of the known laws of physics. This is often where the neutron star becomes most impressive in calm scientific description. It does not violate the laws, it fulfills them with unusual completeness. Effects that are negligible on Earth become dominant. Curvature of space-time, gravitational redshift, extreme compression, rapid rotation, and magnetic intensification all occupy the foreground at once. The remnant is not a place where physics fails. It is a place where physics is hard to ignore. Rotation sharpens this severity into motion. When the stellar core collapses, its spin increases dramatically as its size decreases. The principle is familiar, but the outcome is extreme. Some neutron stars rotate once every few seconds. Others turn dozens, hundreds, or in special cases more than 700 times in a single second. At those speeds, the equator moves with astonishing velocity. The star becomes a compact world in near constant self-sweeping motion, yet it remains stable. That fact alone carries a kind of quiet tension. A mountain on Earth does not circle the planet in a fraction of a second. A city does not spin hundreds of times each second and remain intact. The neutron star does. It is not merely a fast object. It is an object whose internal strength, pressure, and gravity are enough to hold together under rotational conditions that would destroy almost anything else. This makes it feel less like a star in the usual sense and more like an engineered limit. Though no one engineers it, nature builds it through collapse, and nature then permits it to endure. Stability, however, is not simple serenity. A spinning neutron star constantly negotiates between gravity pulling inward and rotation resisting that pull near the equator. Its shape may flatten slightly. Its crust may carry strain. Over time, as the star loses rotational energy and slows, that balance changes. The surface and deeper layers must adjust to a new equilibrium, and sometimes they do so abruptly. Even before those sudden changes are considered in detail, the idea itself matters. The neutron star is not a finished stone left after an explosion. It is a tense and evolving remnant, cooling, spinning down, radiating, and shifting under stresses locked into it at birth. It carries violence forward in a more disciplined form. One of the strangest facts is that such an object can be measured with remarkable accuracy from across the galaxy. Its mass can be estimated through orbital motion if it has a companion. Its size can be constrained through X-ray studies and models of surface emission. Its spin is read directly from the arrival times of pulses. Its magnetic field can often be inferred from how quickly the rotation slows. In this way, the neutron star becomes both inaccessible and intimate. No spacecraft reaches one. No sample returns from its crust. Yet its behavior gives itself away with unusual openness. It is one of the least habitable objects imaginable and one of the most revealing. The more it is measured, the stranger its scale becomes. An object scarcely wider than a city contains more mass than the sun. Its surface gravity would crush any known structure. Its escape speed rises to a substantial fraction of the speed of light. Its magnetic field, in some cases, surpasses by enormous factors anything that can be sustained in laboratories on Earth. Its surface may be smoother than any manufactured sphere because gravity suppresses high relief. It rotates with a steadiness that rivals atomic clocks, yet it originates in an explosion. Each feature seems to belong to a different category of the universe. Precision belongs to clocks. Violence belongs to explosions. Gravity belongs to planets and black holes. Radiation belongs to hot gas. Yet in a neutron star, these qualities meet and remain bound together in a single object. That union is the deeper source of its mystery. If it were only dense, it would already be remarkable. If it were only fast, it would already be memorable. If it were only magnetized, it would already demand attention. But it is all of these at once, and the combination suggests that the usual labels may be too coarse. A neutron star is called a star because it is born from one. But much of what makes a star familiar has been stripped away. It no longer shines through fusion. It no longer breathes outward against gravity in the same living cycle. It persists instead as a residue of balance at the edge of further collapse. That edge may be narrow. Add enough mass or change enough internal conditions, and the remnant may fall past neutron pressure and become a black hole. In this sense, every neutron star may be understood as an object living beside another fate, surviving just short of disappearance. This possibility does not make it unstable in the everyday sense. Many last for millions or billions of years, but it places the entire class in a narrow corridor of existence. They are not simply compact stars. They are survivors of a threshold. From far away, a pulsar appears as a recurring flash, tidy and almost abstract in its repetition. Behind that flash lies a world of pressure so intense that ordinary matter is transformed, a gravity so strong that light bends and time slows, a surface so hostile that structure itself becomes fragile, and a rotation so exact that catastrophe begins to resemble order. The more clearly the object is described, the less natural it feels in the gentle sense of the word. It remains lawful, measurable, and real, yet it seems assembled from conditions that do not usually share the same place. That is where the intrigue begins to deepen. The neutron star is not only the answer to what a pulsar is, it is the beginning of a second uncertainty, because an object this small, this dense, and this severe invites a further thought that observation keeps close but never entirely settles. If the outside is already this extreme, then whatever lies beneath that thin bright surface may be stranger still, perhaps stranger than any outward pulse can fully reveal. The outside of a neutron star gives only a narrow hint of what lies below. From a distance, the remnant can be timed, weighed, and tracked, yet its interior remains hidden behind a boundary thinner than instinct expects. This surface is not the broad boiling atmosphere of an ordinary star. It is thought to be covered by a very slight veil of gas, perhaps no thicker than a human hair if pressed into earthly comparison, though the pressure and heat make that comparison feel almost misleading. Beneath that thin outer layer, gravity presses with such force that irregularities are suppressed. Mountains, in any familiar sense, cannot truly rise there. A bump only a few centimeters high may already be large by neutron star standards. The result is a surface that may be among the smoothest known in the universe, not because it is gentle, but because gentleness has been crushed out of it. The star is polished by force. That calm exterior is deceptive. Under it lies a crust unlike anything found on Earth, and below that crust the matter becomes progressively harder to describe. The descent inward is not a journey through layers that look different in the ordinary way. It is a passage through changing states of compression, where the same basic ingredients are pressed into unfamiliar forms. Near the outermost solid regions, nuclei and electrons still exist in something closer to recognizable order. Atoms as such do not survive intact, but their building blocks have not yet surrendered all ordinary structure. The nuclei are packed tightly into a lattice, a rigid arrangement held together under immense weight, while electrons move more freely between them. Even here the matter is already exotic by any ordinary standard. The star has no room for chemistry as Earth knows it. There are no minerals, no fluids, no gases in the common sense. There is only compressed substance arranged under rules set by extreme density and relentless gravity. The crust is solid, yet it is not a quiet solid. It is strained, loaded, and deeply constrained, its particles forced into positions that depend on pressure as much as identity. As the depth increases, the pressure rises fast. There is no slow easing from one environment to another. Each step inward produces a sharper demand on matter. Atomic nuclei, pressed closer together, begin to capture electrons more readily. Protons and electrons combine, increasing the neutron richness of the material. Nuclei become heavier and stranger, loaded with more neutrons than would remain stable anywhere else. On Earth, such nuclei would decay almost immediately. Here they persist because the surrounding pressure allows them to. Stability itself changes meaning inside a neutron star. A structure that would be impossible in an ordinary environment becomes natural under compression. This shift is one of the quiet marvels of the crust. It suggests that matter has not one fixed identity but a range of possible behaviours, each unlocked by different conditions. The neutron star does not create new laws. It simply pushes existing matter into corners where rarely seen consequences emerge. Deeper still, the nuclei are forced so close that their edges begin to blur into one another. They no longer sit like separate beads in a neat lattice. The competition between forces becomes more intricate. Gravity pushes inward on the whole mass. The strong nuclear force binds matter at very short range. Electromagnetism influences the distribution of charge. Quantum principles restrict how closely identical particles can be packed into the same states. Out of this contest comes one of the most memorable ideas in neutron star physics, a set of structures so unusual that scientists give them almost playful names. The matter in this region may arrange itself into shapes resembling droplets, rods, slabs, tubes, and bubbles. The names attached to these shapes evoke food, not because the region is simple, but because common words become useful when confronting something otherwise difficult to picture. The phrase nuclear pasta enters the language of astrophysics in this way. It sounds light. The reality is not. These structures, if they exist as models suggest, are matter under extraordinary pressure, sculpted not by hand or erosion but by the balance of forces acting at the threshold where the crust gives way to deeper regions. The image is memorable because it joins the familiar and the impossible. Beneath the smooth skin of a dead star, matter may settle into forms compared with noodles and sheets, though each such form is denser and stronger than any material humans have ever known. This is where the crust begins to feel less like an outer shell and more like a record of matter losing its ordinary habits. The names can mislead if taken too lightly. The region is not whimsical. It may represent one of the strongest materials in the universe. Calculations suggest that the crust of a neutron star can bear stress on a scale vastly beyond steel or any earthly alloy. This matters because the crust does not merely exist, it resists. It holds together under rotation, magnetic stress, and long-term evolution. It may crack when those stresses shift, and such cracking may be connected to bursts of radiation, especially in the most strongly magnetized neutron stars. In that possibility, the crust becomes more than a passive layer. It becomes an active participant in the star's behavior, storing tension and releasing it in abrupt changes. A pulse observed from Earth may therefore carry, in some cases, the distant consequence of strain building deep beneath the surface no telescope can truly resolve. The star turns, slows, cools, and readjusts. The crust endures these changes until endurance briefly fails. That image introduces a new kind of unease. The pulsar is not only a rotating clock, it may also be a rigid shell under pressure, one capable of minute fractures whose effects echo across the galaxy as shifts in timing or flashes of high-energy light. The closer the narrative moves toward the base of the crust, the more matter begins to surrender the last familiar hints of separation. Neutrons start to leak out of nuclei and move more freely. The material becomes a mixture of neutron-rich clusters and a growing sea of unbound neutrons. This is a threshold region, neither fully crust nor fully core, and it resists neat description because it combines structure with release. There are still remnants of nuclei, but they no longer monopolize the neutrons. Some of the particles are no longer confined to individual nuclear centers. They drift through the surrounding space in a way that hints at the deeper interior yet to come. In some models, these neutrons may begin to behave collectively as a superfluid, a state of matter that flows without ordinary internal friction. If that happens, then beneath the rigid crust lies not simply compressed solid matter, but a strange partnership between solidity and near frictionless flow, A shell of exceptional strength sits above a layer of uncanny mobility. The contrast is severe and elegant at once. The same star contains a rigid outer body and an inner substance that may move in ways no ordinary liquid can. This possible arrangement becomes important later, because it offers one path toward explaining certain sudden changes in pulsar rotation. If a superfluid component inside the crust stores angular momentum differently from the crust above it, then a transfer between the two may produce the abrupt spin jumps known as glitches. In that case, one of the most precise clocks in the universe occasionally reveals the hidden slippage between a hard outer shell and a deeper, strange fluid. Even before those events are discussed in full, the implication already lingers. The interior of the neutron star is not merely compressed, it is layered in behavior, with each region carrying its own way of yielding, resisting, or flowing under the same relentless gravity. Observers on Earth do not see the crust directly. No image shows its lattice. No probe samples its pasta-like phases. Everything known about it comes through models, nuclear theory, timing behavior, X-ray emission, and the broader logic of what matter must do under such conditions. That leaves room for caution. The crust described by textbooks is plausible and strongly supported in outline, but the exact details may still change as theory improves. The shapes may differ somewhat. The transitions may be smoother or sharper. Unseen ingredients may matter more than expected. Yet uncertainty does not weaken the intrigue, it deepens it. The crust is a place where theory and observation lean toward each other without fully meeting. It is inferred, not seen, and yet the inference is too structured to dismiss. The hidden layers below the surface are real enough to shape measurable behavior, even if their exact architecture remains partly speculative. This is one of the recurring features of neutron star science. The invisible keeps leaving fingerprints. A timing anomaly suggests internal coupling. A burst hints at crustal failure. A cooling pattern hints at thermal conduction through dense matter. Piece by piece, the unseen interior makes itself known through consequences. Still, the deeper the crust is considered, the more the sense of nearing a boundary takes hold. The orderly lattice is gone. The strange geometric phases appear and give way. Free neutrons become common. The distinction between nucleus and surrounding matter weakens. Something fundamental is being surrendered as depth increases. Matter is approaching a point where even the concept of a nucleus may no longer be the right way to describe what exists. The crust, for all its exotic beauty, is therefore also a threshold. It is the last region where remnants of ordinary structure can still be named with some confidence. Beneath it waits the core, where the pressure rises beyond direct analogy and the language of familiar matter begins to thin. The calm, smooth surface hides all of this. The pulses continue. The timings remain precise. Nothing in the regular sweep of radiation openly declares that, under the star's bright outer edge, matter may pass through lattices, through nuclear shapes like compressed geometry, through neutron seepage and superfluid hints, and onward toward a center that current models still struggle to define. The crust does not solve the mystery of the neutron star, it prepares it. It shows that even before the deepest region is reached, matter has already become inventive under pressure, arranging itself into forms that are lawful, probably real, and almost impossible to imagine without the help of metaphor. That is the quiet lesson of the crust. The star is stranger before the center than most objects are at their most hidden point. And every layer that can be sketched with some confidence only sharpens the expectation that the unseen heart below may be stranger still. Below the crust, the neutron star enters a region where the language of certainty begins to soften. The outer layers can be approached with some confidence, at least in broad outline. Pressure rises, nuclei grow strange, free neutrons appear, Structure becomes tense and exotic, yet the matter still offers shapes and phases that can be sketched in a limited way. The core is different. It remains hidden not only by distance and gravity, but by the fact that the physical conditions inside it press directly against the limits of what present theory can handle with ease. The remnant is small enough to fit across a city, and dense enough to hold more mass than the sun. At its centre, the pressure climbs beyond the conditions that can be recreated in any stable way on Earth. Laboratories can smash heavy ions together and briefly glimpse dense nuclear matter in collisions. But those moments are hot, fleeting, and incomplete as analogues. A neutron star core is dense, enduring, and cold by comparison with those collisions, though still unimaginably hot by everyday standards. This difference matters. Matter behaves differently when it has time to settle under pressure. The core is not a flash of compression. It is a sustained environment. That makes it one of the most valuable natural laboratories in the universe, and one of the most difficult to read. The simplest description says that the core is made mostly of neutrons, densely packed together, with a smaller population of protons, electrons, and perhaps other particles balancing charge and pressure. This picture is useful because it captures the name neutron star without straying too far into speculation. But even this basic account is incomplete. Neutrons are not tiny hard spheres stacked like grains. They are quantum objects, and their behaviour at such density depends on forces and exclusions that do not resemble ordinary packing. The exclusion principle, which prevents identical fermions from occupying the same quantum state, becomes central. At ordinary densities, it shapes atoms and chemistry in quiet ways. In a neutron star core, it helps hold up an entire star. The particles resist being crowded into the same conditions, and that resistance contributes to the pressure that opposes gravity. This is one reason neutron stars are often described as being supported by degenerate matter. The phrase sounds technical, but its meaning can be stated simply. The matter is squeezed so tightly that quantum rules, not ordinary thermal motion, provide much of the support. The star is held up not because it burns, but because matter itself refuses complete overlap. That refusal is powerful, though perhaps not infinitely so, if enough mass accumulates. Even it may fail. This is where the neutron star begins to feel like a compromise imposed on matter by gravity. The core is neither ordinary substance nor full collapse. It is a dense truce. That truce may conceal more than one possible arrangement. The pressure at different depths may favour different populations of particles. Near the outer core, the simple picture of neutrons with a smaller admixture of protons and electrons may remain broadly valid. Deeper in, new possibilities emerge. Some models suggest that muons may appear, heavier cousins of the electron created because the density makes their presence energetically favourable. Others suggest that strange baryons called hyperons may form, particles containing strange quarks that rarely appear under ordinary conditions. Their arrival would change the way pressure builds with density, and would alter the maximum mass a neutron star can support. Yet here the models begin to compete. If hyperons appear too freely, they may soften the matter too much, making it difficult to explain the existence of neutron stars already measured to have around 2 solar masses. This tension becomes a clue. Astronomers are not merely guessing at interiors in isolation. Observed masses push back on theory. A star that truly exists excludes some possibilities and constrains others. The invisible core is therefore shaped by measurements made far away. A pulse timing campaign, an orbital calculation in a binary system, or a careful study of X-ray emission can reach inward by logic, even when no instrument sees the center directly. Still, each new constraint narrows the field without fully closing it. One possibility that has long captured attention is the idea that parts of the core behave as a superfluid. In an ordinary fluid, internal friction and viscosity govern how motion spreads and slows. In a superfluid, under the right quantum conditions, flow can occur without the same kind of resistance. This is not fantasy. Superfluidity is observed in laboratory systems such as liquid helium, though never under the conditions found inside a neutron star. If neutrons in the inner regions pair up in a quantum state, analogous in some ways to superconductivity, then a large fraction of the core may move as a neutron superfluid. Protons, meanwhile, may become superconducting, allowing electric current to flow without resistance. These words can sound almost elegant, but the elegance is severe. Inside the dark remnant of a dead star, matter may be colder in behavior than its actual temperature suggests, slipping into collective quantum states on a scale larger than mountains, larger than continents, larger than worlds. The core would then be both crushingly dense and strangely coherent, a place where quantum order is not a microscopic curiosity but a global property. This possibility matters because it offers explanations for observations. Glitches, the sudden tiny speed-up seen in some pulsars, may involve a transfer of angular momentum from an inner superfluid to the crust. The star slows gradually as it loses energy, but the superfluid may not track that slowdown in the same way. It may store a slightly different rotational state, then couple more strongly for a moment, and pass some of that stored rotation outward. A clock that should merely wind down instead jolts forward by a small amount. Such events suggest that the interior is not one unified block. It contains components that communicate imperfectly, with tension building between them. The core, if superfluid, is not passive. It helps govern the star's timing. Yet superfluidity is not the end of speculation. It is the beginning of a deeper opening. Neutrons and protons are themselves made of quarks, bound together by gluons. Under everyday conditions, quarks remain confined inside particles such as protons and neutrons. Under sufficient pressure, some theorists propose that this confinement may weaken, allowing matter to pass into a deconfined state, in which quarks move more freely through a larger medium. This would not mean that the neutron star stops being a neutron star in the broad astronomical sense. It would mean that deep in the core, the substance is no longer best described as distinct neutrons crowded together. It becomes quark matter, perhaps involving up and down quarks, perhaps also strange quarks if the density and interactions allow. The idea is not arbitrary. It follows from the known internal structure of hadrons and from calculations suggesting that extreme density may unlock phases impossible elsewhere. But the uncertainty is large. The details depend on equations that are difficult to solve under these conditions. Some models predict a sharp transition, almost like a hidden boundary within the star. Others allow a smoother crossover. Some suggest exotic mixed phases. A few even entertain the possibility that strange quark matter might be especially stable, raising the old and still unresolved notion that some compact stars could be strange stars rather than conventional neutron stars in the deep sense. Observations have not settled this. The line between dense nuclear matter and deconfined quark matter remains one of the great unsolved boundaries in astrophysics. There is something especially unsettling about this uncertainty, because it applies not to the edges of the universe, but to the center of an object already known to exist in large numbers. The galaxy may contain hundreds of millions of neutron stars, though only a small fraction are seen as pulsars. If even some of them hide quark matter in their cores, then the Milky Way is full of natural containers of a phase of matter never directly touched or observed in isolation. The implication is quiet and large. Whole populations of compact stars may be carrying internal states that remain mostly theoretical, their existence hinted at through mass, radius, cooling, and timing rather than sight. This is one reason neutron stars continue to attract such close attention from observatories and theorists alike. They do not merely tell a story about dead stars, they test the behavior of matter itself. The detection of gravitational waves from colliding neutron stars has sharpened this effort. When two neutron stars spiral together and merge, as in the famous event observed in the late 2010s by gravitational wave detectors and telescopes across the spectrum, the signal contains information about how easily each star deforms under the gravity of its companion. That deformability depends on the stiffness of dense matter, which in turn depends on what the core is made of and how pressure responds to compression. For a brief time, the collision speaks for the hidden interior. It does not deliver a final answer, but it adds a new line of evidence. A neutron star is no longer probed only when isolated and flashing. It is also probed when distorted, torn, and merged. The core leaves fingerprints even in destruction. Cooling offers another path inward. Young neutron stars radiate heat, and the rate at which they cool depends on processes inside the star. If certain particles are present, neutrino emission may carry energy away more efficiently. Superfluid transitions may alter the cooling curve. Observations of some neutron stars suggest episodes of cooling that fit with the onset of neutron superfluidity or proton superconductivity in their cores, though interpretation remains cautious. Again, the pattern repeats. The unseen center reveals itself only through consequences, and each consequence can often be explained in more than one way. No single observation speaks clearly enough. Instead, a web of partial evidence grows. Mass measurements rule out some soft equations of state. Radius estimates prefer certain pressure ranges. Gravitational wave signals constrain deformability. Cooling behavior hints at interior transitions. Glitches suggest dynamic coupling between regions. Magnetaires imply that magnetic and crustal stresses may reach extraordinary levels. Together, these facts make some kinds of core more plausible and others less so, yet a complete map still recedes. There is also the possibility that the core changes over time. A newborn neutron star is hotter and perhaps more chaotic internally than an older recycled pulsar spun up in a binary system. Composition, rotation, temperature, and magnetic history may all influence which phases appear and how sharply they are expressed. This means there may be no single universal neutron star interior. There may be families of interiors, related but not identical, shaped by the specific path each star takes from collapse onward. The phrase neutron star then hides as much as it reveals. It groups together objects that may share an outer category, while differing in deep internal state. A slowly cooling isolated pulsar and a rapidly spinning recycled pulsar may not contain exactly the same core structure even if both produce precise signals. The beam is visible. The interior biography is not. In the calmest view, this uncertainty is not failure, but invitation. The core remains difficult to define because it sits at a crossroads of nuclear physics, particle physics, relativity, and astronomy. Few objects demand so many branches of knowledge at once, yet the more branches gather around it, the clearer the central fact becomes. Something is present there that cannot be reduced to a simple image. It may be a sea of neutrons under quantum tension. It may include superfluid layers and superconducting currents. It may emit hyperons. It may transition toward quark matter. It may do some of these things only in certain mass ranges or ages. The core does not announce its composition directly. It alters timing, mass, cooling, and deformation, and leaves scientists to reconstruct the whole from those traces. That reconstruction grows more sophisticated with every decade, but it still stops short of certainty. Beneath the precise pulses and the smooth exterior, The neutron star may therefore hide one of the least accessible physical environments in nature, an environment where matter stands close to another identity and perhaps partly crosses into it. The strange thing is not only that this hidden core exists, it is that the universe keeps placing it inside objects that can be heard across the galaxy as regular beats of light and radio waves, as if an unknowable centre has wrapped itself in one of the clearest signals in astronomy. A neutron star can remain dense, hot, and rapidly rotating without becoming a pulsar in the observed sense, unless another ingredient sharpens its presence into a signal that reaches across space. That ingredient is the magnetic field. In ordinary experience, magnetism belongs to compasses, laboratory coils, and the quiet pull between small pieces of metal. Even in the larger settings of planets and stars, it usually remains abstract, something inferred through auroras, charged particles, and the behavior of plasma. In a neutron star, magnetism ceases to be a subtle background feature. It becomes architecture. It shapes the space around the remnant, directs the motion of charged particles, controls where energy escapes, and helps turn a compact stellar corpse into one of the cleanest repeating beacons in the sky. The field is not simply strong. It is carried into a range where familiar comparisons begin to fail. During the collapse of the parent star's core, magnetic flux is compressed along with matter. A field that was moderate on stellar scales can become immense when forced into a body only a few tens of kilometers across. The exact amplification depends on the history of the star and on processes during collapse that may twist and intensify the field further, but the outcome is clear enough. The newborn neutron star possesses a magnetic field that can exceed anything sustained on Earth by factors so large that the ordinary language of magnets becomes almost decorative. The field does not merely influence nearby particles, it dominates them. It imposes order in a region where gravity and rotation are already severe. This conjunction is essential. A rotating magnetic field does not remain quiet. If the magnetic axis is tilted relative to the rotation axis, and in many neutron stars it appears to be, then the field sweeps through space as the star turns. That changing electromagnetic structure induces electric fields of enormous strength. Charged particles near the surface are pulled from the crust or created in cascades above it. Electrons and positrons can be accelerated to extreme energies. Radiation pours out along open field lines, especially near the magnetic poles, where the geometry allows particles to escape outward rather than remaining trapped in closed loops. The pulsar beam is born from this system. It is not simply a shaft of light shining from a rotating lamp. It is the visible effect of a magnetosphere, the region around the star where plasma, electric fields, and magnetic structure interact in a highly organized but not fully settled way. The word magnetosphere may sound calm because Earth has one, but the two settings barely resemble each other. Around Earth, the magnetosphere deflects the solar wind and shelters the upper atmosphere. Around a neutron star, the magnetosphere is a violent electromagnetic machine. Its boundaries, currents, and plasma flows determine how the pulsar shines and how it changes over time. Close to the star, the field lines can form closed loops, trapping particles and guiding them in arcs. Farther out, there comes a crucial distance where co-rotation with the star would require motion at the speed of light. Beyond that limit, the field cannot keep matter turning rigidly with the surface. The lines open outward, and energy streams away in a pulsar wind, a flow of relativistic particles and fields that can inflate surrounding nebulae and stir the debris left by the parent supernova. In young energetic pulsars, this wind becomes visible through glowing structures in X-rays and radio emission, a sign that the rotating magnetic engine is feeding its surroundings. The beam seen from Earth is therefore only one part of the star's activity. Much of the energy leaves in forms that do not cross the line of sight as a pulse at all. The remnant spins, radiates, and loses energy continuously, like a wound spring releasing itself through electromagnetic structure. One of the deep attractions of pulsar physics lies in how much is understood and how much remains uncertain within that magnetosphere. The basic framework is well established: rotation, strong magnetic field, and misalignment between axes can produce sweeping beams. Charged particles accelerated along open field lines emit radiation. The star slows because rotational energy is converted into outgoing electromagnetic power and particle winds. Yet the details are still contested in important ways. Exactly where the radio pulses are generated remains a subject of active modelling. Some emission may arise relatively close to the magnetic poles near the stellar surface, while higher energy gamma rays may come from more distant regions in the outer magnetosphere or near the current sheet beyond the light cylinder. The pulse profile, meaning the shape of the signal as it arrives over one rotation, depends on geometry, altitude, plasma behavior, and the observer's line of sight. A simple lighthouse picture explains the repetition, but not the full complexity of what is being swept. Some pulsars show narrow pulses, others show multiple components. Some change profile with time or observing frequency. Some switch on and off in radio wavelengths. Some emit giant pulses, rare and intense flashes far stronger than the average signal. Precision in timing coexist with diversity in emission. The magnetosphere behaves like a machine, but not always like a simple one. The field strength itself can approach regimes where even empty space begins to act differently. Quantum electrodynamics predicts that in extraordinarily strong magnetic fields, the vacuum is not entirely passive. It can become birefringent, meaning that light with different polarization states can travel through it differently, as if the vacuum has gained a subtle optical structure. This effect is far too weak to notice under normal conditions, but neutron stars may provide one of the rare natural settings where it becomes observable. There have been efforts to detect such signatures in the polarized light from isolated neutron stars. The interpretation remains delicate, but the possibility alone is revealing. The magnetic field is not simply acting on matter around the star. At sufficient strength, it may expose rare behavior of the vacuum itself. The emptiness around the remnant is no longer empty in the ordinary sense. Under such a field, it becomes a medium with measurable response. This turns the pulsar and its relatives into more than exotic stars. They become testing grounds for fundamental physics under conditions unavailable anywhere else. The calm repetition of a pulse can therefore conceal a region where the boundary between matter, radiation, and vacuum grows thin. The field also shapes the star's long decline. As radiation and particle winds carry energy away, the neutron star loses rotational speed. Young pulsars often spin faster and possess stronger observable activity. Older ones slow down. Their pulses can weaken or vanish from detection. Some cross an informal threshold, sometimes called the death line, where the conditions needed to sustain particle acceleration and coherent radio emission no longer hold effectively. The star does not disappear. It simply grows quieter. This fate contributes to the hidden population problem. The galaxy likely contains many more neutron stars than the number observed as active pulsars. Some beams miss Earth. Some stars may never have favourable emission geometry for observers here. Others may have spun down past easy detectability. The magnetic engine ages. Its signal changes. The measured pulsars may be only the audible subset of a much larger silent census. Yet silence is not always simple quiet. In the most strongly magnetized neutron stars, the field may become so intense that it does not merely power a stable beam. It can strain the crust, twist the outer field, store energy in magnetic loops, and then release that energy in bursts. These objects are called magnetars, and they occupy a special and unsettling corner of the pulsar family. Their surface magnetic fields, inferred from timing behavior and burst energetics, may reach values hundreds or even thousands of times stronger than those of more ordinary radio pulsars. In such stars, the magnetic field becomes not just a guide for plasma but a reservoir of catastrophic stress. The crust may shift under that stress, or the magnetosphere may suddenly reconfigure. When it does, the star can emit intense X-rays and gamma rays in brief flashes or longer outbursts. Some of these events are among the most powerful magnetic explosions known. They arrive irregularly, unlike the disciplined radio pulse of a standard pulsar, and they make the neutron star seem less like a clock and more like a trapped storm. Yet the same basic object lies underneath a compact remnant of stellar collapse, rotating, dense, magnetized, and only partly understood. The magnetar extends the logic of the pulsar into a more unstable regime. It shows that the same ingredients, pushed harder, can produce not only timing but eruption. This opens an interpretive space that remains active and cautious. Some fast radio bursts, extremely brief and powerful radio flashes detected from distant galaxies, have in a few cases been linked to magnetar activity. One galactic magnetar has produced bursts resembling weaker versions of those mysterious extragalactic signals, strengthening the case that at least some fast radio bursts come from magnetized neutron stars. But the broader population of such bursts is diverse, and the full explanation remains unsettled. The point here is not that magnetars solve every radio mystery. It is that neutron stars continue to extend their reach into phenomena once thought separate. Their magnetic lives may connect them not only to steady pulses and X-ray outbursts, but also to some of the briefest and brightest radio events in the universe. A remnant only a few tens of kilometers across may disturb detectors across whole galaxies. That scale mismatch is one of the recurring astonishments of the subject. It remains astonishing precisely because it is grounded in measurement, not metaphor. Another layer of intrigue comes from the geometry itself. The magnetic axis and rotation axis need not remain fixed forever in simple relation. Precession, field evolution, crustal motion, and long-term torque changes may alter the observed pulse profile or timing in subtle ways. Some pulsars show mode changes, drifting subpulses, or intermittent emission that suggests the magnetosphere can rearrange itself between quasi-stable states. The pulse remains regular in gross timing, yet the detailed pattern of radiation shifts as if the electromagnetic engine is capable of changing gears. This means the pulsar is not always best pictured as a rigid beacon. It may be a dynamic plasma system hovering near multiple allowed configurations. A small change in charge distribution or current flow could alter what distant telescopes receive without any dramatic change in the star's bulk properties. The steady sweep hides inner adjustments. Even the clean signal has moods. This is part of why pulsars are so valued and so difficult. They provide exquisite timing, yet the source of the pulses involves plasma physics under extreme conditions, and plasma rarely behaves with perfect simplicity. The field reaches outward far beyond the star's tiny surface, and builds a region where relativity, magnetism, radiation, and collective particle behavior all matter at once. That region is not directly seen in one glance. It is inferred from pulse shapes, polarization swings, spectra, timing noise, and long campaigns of observation. Here again the invisible leaves structured traces. The magnetic field itself cannot be photographed like a wire pattern in a school demonstration, but its existence is written into the slowing spin, into the polar cap heating, into the pulse polarization, into the nebula fed by the wind, into the sudden gamma-ray flare of a magnetaire, and into the alignment or misalignment required for the beam to be seen at all. The field shapes everything, and yet remains itself a hidden form, known by action. In a calmer universe, that might be enough. But neutron stars refuse calm completeness. There is still no single agreed model that captures every pulsar across every wavelength and every stage of life. Radio emission remains especially elusive in its fine details. Coherent radiation, the process by which many particles emit in a coordinated way strong enough to explain the brightness temperatures observed, is not fully pinned down. Different classes of pulsars may use different dominant mechanisms. Some beams may form high, some low. Some pulse variations may reflect small-scale plasma turbulence, others larger reorganizations of the magnetosphere. The object remains precise in timing and difficult in explanation. This duality is perhaps nowhere more visible than in the magnetic story. The broad design is firm. The detailed functioning is still alive with uncertainty. A rotating magnetized neutron star generates beams and winds and slowly spends its rotational energy. That much is secure. But the exact pathways by which particles are accelerated, by which radio coherence emerges, by which magnetar fields twist and break, by which the vacuum itself responds to extreme fields, all remain areas where observation meets theory without fully settling into final form. The pulsar thus becomes a lesson in layered understanding. It is possible to know what kind of object produces the pulses, and still remain unsure how its electromagnetic life is organized in detail. The more closely the magnetic system is examined, the more it appears less like a static field painted onto a star, and more like a living structure of charge and motion wrapped around a dead one. Beneath the beam lies a compressed remnant of stellar collapse. Around it lies a restless magnetic architecture, invisible and immense in effect. The pulses crossing Earth are only the narrow moments when that architecture turns in the right direction. Everything else happens in the dark, in silence from the observer's point of view, as the neutron star keeps rotating within its cage of field lines, bending particles into paths, feeding nebulae, bursting in rare magnetic fury, and perhaps even making empty space itself behave in unfamiliar ways. The most disarming feature of a pulsar is not its violence, its density, or even its origin in stellar collapse. It is its order, from Earth. The remnant often first enters the record not as a storm but as a schedule. A pulse arrives, then another, with such steadiness that the star begins to resemble a clock placed inside the galaxy. This is not a loose resemblance. Some pulsars, especially the fastest and most stable among them, rival the precision of the best human timekeeping devices over long intervals. Their pulses can be predicted so well that even tiny deviations become meaningful. A shift too small for ordinary thought can matter to astronomers tracking the beat across months and years. The neutron star is therefore one of the strangest combinations in nature. It is the wreckage of catastrophe behaving with almost ceremonial regularity. That regularity begins with rotation. The beam does not choose when to arrive. It arrives when the star turns. Each pulse is a mark of angular momentum written into radiation. As long as the spin remains stable, the pulse train remains stable. This turns the pulsar into something rare in astronomy, an object whose timing can be followed not merely in broad cycles like seasons or orbits, but in individual intervals counted with exquisite care. Once enough pulses are recorded, astronomers can build a timing model that predicts the arrival of later pulses while correcting for Earth's own motion, for the pulsar's motion through space, and for any orbital motion if the star belongs to a binary system. The result is not just a list of flashes, it is a map of rotation. In some cases, the map becomes so exact that leftover discrepancies reveal subtle effects from gravity, interstellar plasma, or the pulsar's own internal unrest. Precision becomes a form of listening. The cleaner the beat, the more clearly any imperfection stands out. This is why pulsars are often described as cosmic clocks. The phrase is useful, but it hides an important tension. A manufactured clock is built to be regular. A pulsar is regular as a consequence of collapse, conservation, magnetism, and internal structure. Its precision is not designed, it emerges. That alone would already be remarkable. Yet the deeper intrigue lies in the fact that the clock does not remain perfectly smooth forever. It drifts, it slows, it jitters, it occasionally jumps. The more carefully it is timed, the more the hidden complexity of the star begins to show through the discipline of its beat. The first and most universal change is the gradual loss of speed. A pulsar is born with rotational energy, and as it emits radiation and drives particle winds, it spends that energy. The spin rate decreases, the beam still sweeps, but each full turn takes a little longer than before. This slowdown is usually tiny from one day to the next, yet over years and decades it is unmistakable. The process is calm enough that astronomers can measure not only the period of the pulses, but the rate at which that period changes. From this, they infer age in a rough characteristic sense and estimate magnetic field strength under standard assumptions. The pulsar that seems perfectly steady is in fact winding down. It is a clock that carries its own exhaustion. This slow breaking is itself a form of story. A young pulsar may rotate many times each second and lose energy rapidly. An older one may turn once in a fraction of a second, or more slowly still, spending its remaining spin with greater restraint. The beam becomes the trace of a long decline. Yet the decline is not always smooth in detail. That is where the mystery begins to sharpen. One way to describe pulsar timing is to say that it reveals how nature behaves when nearly perfect order is placed under hidden strain. The pulse train can be astonishingly predictable for long periods, then depart from that prediction in ways that are too structured to dismiss and too small to see without sustained attention. This is especially true in the case of glitches, the sudden and slight increases in rotational speed observed in some pulsars. A star that should be slowing down calmly instead gives a tiny forward jolt. The change is minute in ordinary terms, but for an object timed with such care it is dramatic. The pulse arrives a little earlier than expected, and the timing solution must be rebuilt around the new behaviour. The effect can then partially relax, or settle into a new pattern. These glitches are among the clearest signs that the neutron star is not one rigid piece turning in perfect unity. Something inside it is storing motion differently from the crust, and then handing some of that motion back. This possibility points toward the superfluid interior discussed earlier. If parts of the inner star form a superfluid threaded by quantized vortices, then that fluid can rotate in a way unlike any ordinary liquid. The vortices may pin to the crust or to structures within it, resisting the gradual slowdown imposed on the outer layers by electromagnetic braking. Over time, a lag can grow between the superfluid's preferred rotational state and the more slowly turning crust. Then, under the right conditions, many vortices may suddenly unpin and move. Angular momentum is transferred, the crust spins up a little, the pulsar glitches. This idea is widely used because it fits the existence of abrupt changes and links them naturally to internal quantum behaviour on a stellar scale. Yet the full process is still not completely settled. Different pulsars glitch differently. Some show frequent small events, others show rare large ones. The recovery after a glitch can vary. The Vela pulsar, one of the best-known examples, has exhibited repeated glitches that have become central to theories of neutron star interiors. Even so, the detailed trigger remains uncertain. The crust may be involved not merely as a passive anchor point, but as a stressed solid capable of shifting in tiny star quakes. A quake could alter the shape of the crust slightly, or disturb the pinned vortices, helping initiate the event. The glitch then becomes a layered phenomenon, part superfluid transfer, part crustal adjustment, part magnetic and rotational bookkeeping. The calm clock has a hidden mechanism, but that mechanism is not fully transparent. A further strangeness appears in what astronomers call timing noise. This is a broader and often more irregular departure from a simple spin-down model. Some pulsars do not just glitch in sudden discrete steps, they wander slightly in their timing, as if the rotation carries a low level of roughness. The causes may differ from star to star. Magnetospheric changes can alter the torque acting on the star. Internal coupling between layers may shift gradually. Small unmodelled events may accumulate. In a few pulsars, changes in pulse shape and changes in slowdown rate appear linked, suggesting that the magnetosphere itself can switch between states and slightly modify the braking. The clock remains precise enough to notice the difference, but not so sealed from its environment that nothing disturbs it. This is one of the quiet revelations of pulsar timing. Precision does not imply simplicity. An atomic clock in a laboratory can be isolated, a pulsar cannot. It is embedded in a magnetosphere, sometimes in a binary system, always in an evolving internal condition, always slowing under the loss of energy. Its regularity is therefore a structured regularity, not a sterile one. That makes every deviation informative. There is also a more formal measure of the slowdown called the braking index, which compares how the spin rate and its derivatives change with time. In the simplest magnetic dipole picture, the braking index would take on a certain value, but observed pulsars often depart from this expectation. The discrepancy suggests that the idealized model is not the whole story. Magnetic field strength may evolve. The angle between magnetic axis and rotation axis may change. Particle winds may contribute differently than assumed. Internal and external torques may not remain constant. In other words, the pulsar does not break like a perfect textbook rotor. It breaks like a real compact star with a complex field and a living magnetosphere. The measured departure becomes another sign that the star's apparent simplicity hides layers of active physics. Some of the most astonishing precision is found in millisecond pulsars, the old neutron stars that have been spun up by accreting matter from a companion. These pulsars rotate hundreds of times each second and often show extraordinary stability. Their pulse arrival times can be tracked so accurately that they form the basis of timing arrays used to search for gravitational waves of very long wavelength. That application belongs to a wider story, but even within the pulsar itself the implication is striking. An object formed in supernova violence, then aged, then recycled by matter drawn from a neighbouring star, can become one of the most stable rotators known. The history is messy, the beat is clean. This contrast keeps returning in pulsar science, as if the object continuously separates appearance from origin. The beam is simple, the biography is not. Binary pulsars deepen the timing story further because orbital motion modulates the pulses in calculable ways. As the neutron star moves toward or away from Earth in its orbit, the arrival time shifts slightly through the Doppler effect and changing light travel time. By fitting these variations, astronomers measure the orbit with exceptional precision. In some systems, relativistic effects become visible. The orbit may precess. Signal delays caused by curved space-time near the companion can appear. The orbit may shrink over time as energy leaves through gravitational waves, as famously shown by the binary pulsar discovered by Russell Hulse and Joseph Taylor, long before direct detections of gravitational waves from merging compact objects. Pulsar timing in this system provided compelling indirect evidence that such waves were real. The clock did more than keep time. It exposed the slow leaking of energy from space-time itself. This is one of the deepest reasons pulsars hold such status in astronomy. Their precision allows them to reveal effects that would otherwise remain buried. Yet even here the mystery does not fully yield. A binary pulsar can be modelled with extraordinary success, and still the neutron star at its centre may hide an uncertain core, an evolving magnetic field, and glitch-capable internal layers. The timing solution may be magnificent, and the object may remain in part unread. Some pulsars even vanish and return. Intermittent pulsars switch their radio emission off for stretches of time, then resume. Rotating radio transients emit sporadic bursts rather than a steady pulse train. In such cases, the clock seems to step behind a curtain and reappear. The star is still turning, but the emission mechanism is no longer continuously visible. This again points to the magnetosphere as a system capable of changing state. The beam is not simply painted onto the rotation. It depends on plasma conditions that can fail, recover, or reorganize. A pulsar can therefore be rotationally steady while observationally elusive. The timing remains latent even when the signal is absent. This makes the source feel more strange, not less. It is as though the clock continues in darkness and only occasionally lets its face be seen. The great lesson of Section 7, though it never states itself outright, is that precision and fragility are not opposites in a pulsar. They coexist. The beat is real and can be astonishingly stable. The slowdown is measurable and usually smooth. Yet the deeper one listens, the more the star reveals a structure under stress, a magnetosphere capable of rearrangement, and an interior that may hand momentum outward in sudden acts. The perfect cosmic metronome begins to sound less like a rigid mechanism and more like a negotiated order sustained between crust, core, field, and radiation. Each pulse says that the star has turned once more. Each glitch says that something inside has not turned quite as simply as it seemed. The timing residual, the breaking anomaly, the intermittent silence, the abrupt step forward in rotation, all of these are small disturbances against a larger regularity, and because the regularity is so good, the disturbances become precious. In many branches of astronomy, noise obscures the source. In pulsar timing, the source uses noise to confess. The tiniest mismatch between prediction and arrival can point toward hidden fluid, crustal failure, magnetic state changes, orbital effects, or the influence of curved space-time. A dead star becomes a diagnostic instrument. Its pulse train is read like a code, though not a code made by intention. It is the structured remainder of physics working under pressure, with each irregularity opening a narrow path inward. That is why the pulsar clock never truly becomes familiar. The longer it is observed, the more it demonstrates that perfect repetition is only the visible skin of a deeper and less settled reality. Pulsars do not remain one uniform class once enough of them are observed. At first, the basic pattern seems simple. A neutron star forms, spins, carries a magnetic field, and sends beams across space. Yet as the catalogue grows, that pattern begins to branch. Some pulsars are young, energetic, and still surrounded by the glowing remains of the supernova that created them. Some are old and faint, turning with slower dignity after millions of years of steady braking. Some spin with almost unbelievable speed, completing hundreds of rotations each second. Some live alone, some exist in pairs. Some feed on nearby stars, some erode their companions, some fall quiet, some erupt in X-rays and gamma rays with the erratic force of magnetars. The family resemblance remains visible, but it is no longer enough. The neutron star becomes a class with its own internal diversity. and each subgroup carries a different version of the same unresolved story. The most natural starting point is the ordinary young pulsar, though ordinary is only a relative word here. These are the remnants born with considerable rotational energy and magnetic strength, often still embedded in or near the nebulae left by their supernova. The crab pulsar is the emblem of this youth. It rotates many times each second, powers a luminous wind nebula, and radiates across the spectrum from radio waves to gamma rays. It is not only a pulsar, it is a central engine still visibly shaping its environment. In such objects, the connection between stellar death and compact remnant remains easy to see. The surrounding cloud expands outward, while the neutron star continues to turn at the centre. As if the supernova has not fully finished speaking, the Vela pulsar offers another young example, notable not only for its age and emission, but for its glitches, which make it a key witness to the unsettled interior. These young pulsars feel like open wounds in the galaxy, still active, still shedding energy, still close in time to the collapse that made them. Yet even among the young, differences appear. Some are easy radio sources, others are brighter in X-rays or gamma rays. Some seem comparatively clean in their pulse shapes, others display complicated profiles. Youth does not erase individuality, it only sets the initial conditions. With time, many pulsars slow, their periods lengthen, their luminosity in certain bands declines. The magnetic engine continues to work, but less vigorously. The beams may remain detectable for millions of years, yet the object gradually moves into a quieter phase. These older isolated pulsars form a large part of the known population. They are the long survivors of earlier violence, still turning, still pulsing, though with less extravagance than their younger kin. In a broad timing diagram, they occupy a different region from the fastest recycled pulsars and from the youngest energetic ones. The diagram itself becomes a kind of family portrait, showing spin period against spin down rate, with clusters that hint at evolutionary pathways. The slow and the fast are not merely different at random. They often carry different histories. The fastest pulsars of all introduce one of the most elegant and improbable transformations in the field. These are the millisecond pulsars, objects spinning so rapidly that the first encounter with their periods can feel almost absurd. A dead star, denser than the sun and no larger than a city, completes a full turn in a few thousandths of a second and does so with astonishing stability. Such a state is not usually explained as a birth condition alone. In many cases, these pulsars are thought to be recycled. They begin as ordinary neutron stars, perhaps slowing over immense spans of time, then later find themselves in binary systems where matter from a companion star flows toward them. This matter carries angular momentum. As it spirals in through an accretion disk, it transfers that momentum to the neutron star and gradually spins it up. What was once a slower remnant becomes a rapid rotator again, though now older, often with a somewhat weaker apparent magnetic field and a cleaner, more stable timing behavior. The idea that a star can die, slow, feed on a companion, and return as one of the finest clocks in the galaxy carries a certain quiet astonishment. It suggests that a neutron star is not fixed in the role assigned at birth. Under the influence of a neighbour, it can be remade. Binary systems therefore become central to pulsar evolution, not as side stories but as workshops of transformation. The companion star can be large or small, ordinary or degenerate, and the exact path depends on mass transfer, orbital separation, and time. Some systems host white dwarf companions left behind after the recycling phase is complete. Others remain more active. In certain cases, the pulsar and companion create a more hostile arrangement. The pulsar's intense wind can begin stripping matter from the nearby star, gradually ablating it. This gives rise to the evocative classes known as Black Widow and Redback systems, In these, the neutron star has not merely accepted matter from its partner, it now threatens the partner's survival, heating and eroding it with radiation and particle winds. The names are dramatic, but the physics beneath them is sober and severe. A compact remnant spun up by accretion may then turn against the donor that helped revive it. Eclipses, orbital variations, and changing conditions in the outflowing material add complexity to the observed pulses. The family portrait becomes more layered. Some pulsars live in companionship, some reshape companionship into slow destruction. The existence of transitional millisecond pulsars deepens this branch even further. These are systems observed switching between an accretion-powered state and a radio pulsar state, as though caught in the act of changing identity. For a time, the inflowing matter dominates, producing X-rays and suppressing ordinary radio pulsations. Later, the accretion weakens or halts, and the neutron star re-emerges as a radio pulsar. This offers rare direct support for the recycling picture. The star is seen moving between modes rather than being classified only after the fact. Yet even here the transitions are not fully simple. The exact way matter interacts with the pulsar magnetosphere near the switch remains a rich area of study. The neutron star seems capable of balancing near a threshold between being fed and pushing matter away, between being wrapped in accretion flow and announcing itself with a beam. Such systems feel less like settled categories and more like weather patterns in compact binary form. They remind the observer that neutron stars can inhabit changing states over humanly observable timescales. Then there are magnetaires, which at first glance almost seem to belong to a different subject. Their magnetic fields are inferred to be so enormous that the star's behavior departs sharply from the calm regularity often associated with pulsars. They can still rotate with measurable periods and slowdowns, and some do show pulsar-like emission at times, but their defining trait is their magnetic violence. They emit bursts and flares of X-rays and gamma rays, sometimes with giant eruptions that briefly outshine nearly everything else in the high-energy sky. The standard pulsar loses energy mainly through steady rotation-powered processes. The magnetar appears to draw much of its activity from magnetic energy itself. The field is not merely a guide for beams. It is a reservoir capable of rearrangement and release. Yet magnetars are not completely separated from the pulsar family. The boundaries blur. Some high magnetic field radio pulsars seem to bridge the gap. Some magnetars have shown transient radio pulsations. The categories remain useful, but they do not seal off the possibilities. The family resembles a landscape with hills and valleys, rather than boxes with hard walls. Different birth fields, ages, spin rates, and evolutionary paths may move a neutron star through different visible behaviors across time. Another part of the family consists of the so-called central compact objects, neutron stars found near the centers of supernova remnants that emit X-rays but often lack obvious radio pulsations and appear to have comparatively weak external magnetic fields. Their nature remains somewhat puzzling. They are clearly compact remnants, but they do not always behave like the textbook pulsar. Some may have buried magnetic fields submerged by fallback material after the supernova, fields that could re-emerge later. If so, the visible behavior of a young neutron star may conceal a different long-term future. The observed type at one age does not always reveal the whole life ahead. In this way, the classification of neutron stars becomes not only a sorting system, but a map of incomplete understanding. Some objects fit established pathways neatly. Others seem to pause between pathways or hint at hidden variables not yet fully constrained. Rotating radio transients add another unsettled note. These neutron stars announce themselves not with a continuous train of easily folded pulses, but with sporadic radio bursts separated by long quiet intervals. Whether they are simply pulsars in an extreme emission state, older objects near the edge of radio death, or part of a more distinct behaviour pattern remains a matter of interpretation. The pulses are real, the category is useful, but the boundary between transient and ordinary remains porous. Once again, the family expands by refusing to become too tidy. The star remains a neutron star, yet the beam does not behave as expected. The object slips in and out of detectability, and the observer is left to infer the full rotation from scattered signs. This pattern of partial visibility runs through the whole field. A pulsar is often defined by what reaches Earth, but Earth only sees a geometry-dependent selection of what compact remnants actually are. The family picture is therefore shaped by detection bias. Narrow beams miss the planet. Faint old pulsars drop below instrument sensitivity. High-energy objects may be easier to find in one band than another. A neutron star that emits mostly in gamma rays may remain invisible to radio surveys, and vice versa. The catalogue is rich, but not complete in any simple sense. What looks like a family tree is also partly a result of how and where instruments are able to listen. Modern observatories have widened this view. Radio telescopes such as Parkes, Arecibo in its operational years, FAST in China, Meerkat in South Africa, and the arrays feeding the Future Square Kilometre Array project have all contributed to enlarging the census. Space missions, including NASA's Fermi Gamma Ray Space Telescope, have revealed pulsars bright in gamma rays, including some scarcely visible in radio. The Neutron Star Interior Composition Explorer on the International Space Station has used X-ray timing to probe hotspots and constrain masses and radii. Each new instrument adds branches to the family portrait while also dissolving old assumptions about which branch is central. The more wavelengths are included, the more neutron stars appear not as one class with odd exceptions, but as a spectrum of compact behaviours shaped by environment, age, magnetism, and chance alignment. Among the most haunting members of the family are the pulsar planet systems. The first confirmed exoplanets ever discovered are found not around sun-like stars but around a pulsar, PSR B1257 +12. This fact still carries a strange stillness. A supernova destroys the parent star's former planetary system, or at least should seem likely to do so, and yet small bodies are later found orbiting the compact remnant. Their exact origin may involve survival, fallback material forming a second-generation disk, or other complex pathways, but whatever the route, the result is unsettling. Worlds can exist around a pulsar, though they do so in one of the least gentle environments imaginable. The first exoplanets known to science are not found in a place that feels fertile. They are found in the aftermath of stellar death. That discovery enlarges the family theme beyond neutron stars themselves. The pulsar is not only shaped by companions and environments, it can also host them. This does not make the system inviting, it only makes the universe less intuitive. By the time all these branches are held together in one view, the word pulsar begins to sound like an entrance rather than a definition. It introduces the observer to a set of related compact remnants, whose lives diverge and reconnect in ways that no single narrative fully captures. Some are newborn and blazing with spin-down power. Some are ancient and precise, polished by accretion into millisecond clocks. Some are solitary. Some are in binaries that nourish them, eclipse them, or slowly consume a partner. Some are magnetically overdriven and eruptive. Some are only intermittently visible. Some hide behind unusual X-ray properties. Some host planets. Each subgroup explains part of the larger picture and complicates the rest. The neutron star is not simply born, flashes and fades. It can be reborn through accretion. It can quiet into near invisibility. It can change emission state. It can become a laboratory for binary gravity. It can host small worlds in the ashes of its first catastrophe. The family of pulsars is therefore not a closed taxonomic exercise. It is a record of how one basic kind of remnant responds to different histories. The same collapsed core, given a different companion, a different field, a different age, or a different line of sight, can become a very different astronomical character. This is why every new pulsar survey tends to enlarge the sense of mystery as much as the sense of order. Each new member belongs to the family. Each new member also suggests that the family is broader, less final, and more inventive than it had seemed the year before. For all their hidden interiors and invisible field lines, pulsars ultimately become part of astronomy through acts of observation that are concrete, patient, and often surprisingly indirect. They are not usually seen first as tiny stars in a beautiful image. They enter the record as measurements. A radio telescope listens to a patch of sky and finds a repeating beat. A gamma-ray instrument counts photons and discovers a pattern in their arrival times. An X-ray observatory detects hotspots sweeping in and out of view on a compact object too small and distant to resolve directly. A timing array compares many pulses over years and searches for shared deviations in their beats. A binary system reveals itself through delays, orbital shifts, and the slow changing shape of an ellipse traced in time rather than in sight. Pulsars are among the clearest examples in astronomy of how an object can become better known by rhythm than by image. The observer does not simply look at a pulsar. The observer waits for it, folds its repeated signal, and lets its hidden form emerge from recurrence. This gives the whole subject a distinct atmosphere. Some astronomical discoveries arrive as pictures that immediately persuade the eye. Pulsars arrive as disciplined patterns that persuade the mind first and the imagination later. The earliest discoveries depend on radio astronomy, because the pulses are strong there, and because radio telescopes, with their large collecting areas, are well suited to catching faint repeating signals from deep space. A dish or array scans the sky and records variations in received power over time. At first, the data can look almost featureless, a noise-like stream where the universe and Earth contribute together. But after the correct adjustments are made, especially the correction for dispersion caused by free electrons in interstellar space, a sharp pulse can appear. This dispersion is itself part of the observational story. Radio waves of different frequencies do not all travel through the galaxy in exactly the same way when diffuse ionized gas lies along the path. Lower frequencies are delayed more than higher ones. A pulsar signal therefore arrives smeared across frequency unless this effect is removed. Once corrected, the beat becomes crisp. That process does more than recover the pulse. It provides an estimate of how much ionized material lies between Earth and the pulsar. Even before the neutron star is fully interpreted, the signal has already begun measuring the galaxy between source and observer. The pulse is both object and probe. This is one reason pulsar astronomy becomes so powerful. Every observation contains more than one layer of information. The pulse period reveals the rotation, the slowdown reveals the expenditure of energy, the dispersion reveals the interstellar medium, the polarization reveals the magnetic geometry and the plasma conditions along the way. The fine timing reveals orbital motion if a companion exists. Scintillation, the twinkling of the radio signal caused by interstellar irregularities, reveals structure in the material between stars. A pulsar is therefore never seen in isolation. Its signal reaches Earth carrying marks not only of the neutron star but of the space it crosses. The observer learns about the source and the intervening galaxy at the same time. That double role has shaped the entire development of the field. Large surveys conducted with major radio facilities steadily expand the known pulsar population. Parks in Australia contributes hugely to the census for decades. Arecibo, while it operates, provides extraordinary sensitivity and helps find and time many important systems, including some of the most precise millisecond pulsars. The Green Bank Telescope, FAST in China, Meerkat in South Africa, and earlier instruments such as the Lovell Telescope continue or extend this tradition. Each survey searches wide regions of sky and applies increasingly sophisticated algorithms to separate real celestial periodicity from terrestrial interference. This is not a trivial task. Earth is noisy. Satellites, transmitters, electrical systems, and local devices all produce patterns that can masquerade as something astronomical. The history of pulsar observing therefore includes a long discipline of discrimination. A real pulsar must show celestial dispersion, consistent sky position, and behavior that survives repeated independent observations. In this sense, the observational life of a pulsar begins with skepticism. Only after the signal has resisted every ordinary explanation does it begin to count as a new star. Once found, the pulsar often becomes the subject of prolonged attention. Timing campaigns can last years or decades. This long patience turns raw detection into deep knowledge. It is how the slow shrinking of a binary orbit becomes visible. It is how tiny glitches are measured. It is how intermittent changes in pulse profile are tied to torque changes. It is how planets around pulsars are found, not by direct imaging, but by the small and regular irregularities they impose on the arrival times of the pulses. The discovery of the first confirmed exoplanets in orbit around a pulsar follows exactly this logic. The timing is so precise that the tug of small orbiting bodies leaves a measurable signature. The result is one of the most unsettling achievements in early exoplanet science. The first worlds known beyond the solar system are not found beside a calm main sequence star, but beside a neutron star, a remnant of collapse and explosion. Observation makes this possible not by showing the worlds in light, but by hearing their influence in the beat of a dead star. The precision required is extraordinary, yet once again the pulsar makes it available. Binary pulsars expand observational power further because orbital motion introduces effects that are rich with information. When a pulsar orbits a companion, the path length to Earth changes through the orbit, and the pulse arrival times shift accordingly. This allows the orbital period, shape, size, and orientation to be inferred with remarkable accuracy. In relativistic binaries, additional effects appear. The orbit can precess. Time delays can occur when the pulse passes through the curved spacetime near the companion. The orbit can gradually contract as energy leaves through gravitational radiation. The celebrated binary pulsar discovered in the 1970s becomes the first great example of this last effect. Over years of timing, the orbital decay matches the prediction of general relativity for energy loss through gravitational waves. Long before laser interferometers directly detect such waves from merging black holes and neutron stars, pulsar timing has already revealed their influence through the slow tightening of an orbit. This observational achievement matters not just because it confirms theory, but because it shows what pulsars can do as tools. They're not only objects to be explained, they're instruments built by nature, precise enough to test the behavior of space-time. Radio observations remain central, but they are not the whole story. Pulsars also reveal themselves across the electromagnetic spectrum, and each band highlights a different region or process. X-ray observatories such as Chandra, XMM Newton, and NICER examine hot surface regions, pulsar wind nebulae, and magnetar outbursts. X-ray pulse profiles, especially when modelled with relativistic light bending near the neutron star, help constrain the mass and radius of the object. This becomes one of the best available ways to press inward on the equation of state of dense matter. The hot spots at the magnetic poles sweep in and out of view as the star rotates, and the exact shape of the observed signal depends on the star's compactness and geometry. Thus, an instrument watching X-rays from a point of light on the International Space Station can infer something about matter at densities beyond terrestrial reach. The observation seems gentle. The implication is severe. Gamma-ray astronomy adds another dimension. The Fermi Gamma-ray Space Telescope reveals a rich population of gamma-ray pulsars, including some not first known as radio sources. This matters because it shows that the geometry and emission zones of pulsars can differ in ways that make one waveband accessible, while another remains difficult. The gamma-ray sky contains neutron stars whose beams or radio conditions do not favour straightforward radio discovery. Again, the family broadens through observation. The pulsar, once imagined mainly as a radio lighthouse, becomes a multi-wavelength object with complex magnetospheric structure. The signal at one energy may come from one altitude, the signal at another energy from another. Pulse shapes can differ across bands, and those differences become clues to where and how radiation is produced. Optical observations, though much rarer because pulsars are faint in visible light, have still played important roles. The Crab pulsar is again the classic case, pulsing in visible wavelengths and allowing direct demonstration that the object's beat crosses many parts of the spectrum. That a dead stellar core can flash visibly from thousands of light-years away, while turning dozens of times each second, remains one of the quietly surreal facts of astronomy. The eye alone cannot usually take in the pulse without instruments and careful processing, yet the visible photons are there, joining the radio, X-ray, and gamma-ray emissions as different expressions of the same compact engine. Surrounding structures become observable too. Chandra images show bright torus-like features and jets in pulsar wind nebulae, especially around energetic young pulsars. These are not the beam itself, but the aftermath of the pulsar wind striking and energizing surrounding material. The neutron star therefore writes its presence not only in pulses but in broader shapes carved into its local environment. In some cases, the pulsar moves rapidly through space, likely kicked during the supernova, and creates a bow shock in the surrounding medium. The remnant then looks almost like a compact ship driving through interstellar gas, leaving a structured wake. Observation broadens from the beat of the star to the disturbed space around it. This widening is important because it prevents the pulsar from becoming too abstract. The source is not just a period and a derivative, it is a body with a motion, a wind, a history, and in some cases a remnant cloud still remembering its birth. Modern pulsar astronomy also depends increasingly on computation. A survey no longer produces just a manageable stream of candidate signals that can be inspected by a few eyes. It produces enormous volumes of data requiring automated search pipelines, machine learning classifiers, and careful statistical filtering. Fast rotation, binary acceleration, intermittent emission, scattering, and terrestrial interference all complicate the search. Some pulsars hide because their orbits smear the signal over the duration of an observation unless acceleration is accounted for. Others are faint and require repeated passes or stacking methods. Some are found first through citizen science efforts or reanalysis of archival data. Observation here becomes a collaboration between hardware, software, and persistence. A pulsar may exist in old data for years before the right method pulls it out. The sky does not always surrender its clocks immediately. There is another branch of observation that carries a quieter grandeur. Pulsar timing arrays use networks of extremely stable millisecond pulsars spread across the sky as a galactic scale detector for low-frequency gravitational waves. The idea is subtle. If a long wavelength gravitational wave passes through the region between Earth and the pulsars, it should slightly alter the arrival times of pulses in a correlated way across the array. The effect on any single pulsar is tiny and ambiguous. The correlated pattern across many pulsars is the prize. Recent years have brought increasingly persuasive evidence for a common low-frequency signal, consistent with a gravitational wave background. likely arising from many pairs of supermassive black holes in distant galaxies. Here the observation becomes almost difficult to absorb. Small dead stars inside the Milky Way, timed over years with extraordinary care, begin to reveal the collective influence of enormous black hole binaries spread across the cosmos. The pulsar does not merely tell its own story. It becomes a reference point against which the deeper background of the universe trembles. This use of pulsars sharpens a central theme running through the whole subject. The better the signal is understood, the more it reveals things other than itself. Yet observation also keeps the sense of incompleteness alive. Not every pulsar fits neatly into the available models of emission. Not every timing irregularity is understood. Not every X-ray pulse profile yields a unique solution. Distance estimates can remain uncertain. Beaming geometry hides much of the population. The interstellar medium can scatter or disperse signals in ways that complicate interpretation. Magnetars can burst unpredictably. Fast radio bursts tempt connection and resist full assimilation. Even the largest catalogues almost certainly represent only a fraction of the neutron stars in the galaxy. The observational view is powerful, but it is selective. It illuminates some lines of sight, some wave bands, some ages, some geometries. It leaves much unlit. That partial nature is part of why pulsar astronomy remains alive with possibility. A new survey method, a more sensitive array, a better timing baseline, or a lucky detection in another band can still alter the shape of the subject. The observer listening to pulsars is therefore never only confirming old knowledge. The observer is also testing the edges of the known family. Every confirmed pulse is a fact. Every new pulsar is also a change in the map, seen from Earth. Then, pulsars are not simply blinking stars. They're observed through radio dishes, space telescopes, timing residuals, orbital fits, polarization swings, nebula structures, and patient years of repeated measurement. They are heard, counted, modelled, corrected, and cross-checked across wavelengths. They reveal planets, companions, winds, glitches, relativistic orbits, and perhaps a background tremor of gravitational waves. Yet after all this, the compact object itself remains a tiny distant remnant whose interior is still inaccessible to direct sight. Observation brings the pulsar very close in one sense and leaves it remote in another. It can be timed more precisely than almost anything else in the sky, and still its deepest matter remains hidden. That is perhaps the most characteristic observational truth of all. The more clearly the beat is heard, the more sharply the silence at the centre comes into view. By the time pulsars have been followed through their birth and collapse, their crushing density, their hidden crust and uncertain core, their magnetic architecture, their timing irregularities, their family branches, and the long history of their observation, they begin to stand in astronomy as more than unusual stars. They become tools. This practical role does not reduce their mystery, it deepens it, because the very properties that make them useful are the same properties that remain only partly explained. Their stability makes them clocks, yet their glitches hint at interior states still uncertain. Their compactness makes them laboratories for gravity, yet the matter producing that compactness is not fully known. Their beams let them guide measurement across the galaxy, yet those same beams reveal only a geometry-dependent fraction of the hidden population. In this way, the pulsar becomes a rare object that grows more scientifically valuable, in direct proportion to how incomplete the full understanding remains. One of the clearest uses of pulsars lies in gravity itself. General relativity predicts specific effects in strong fields and in compact binary motion, and pulsars allow those effects to be tested under conditions very difficult to replicate anywhere else. The famous binary pulsars demonstrate that orbits lose energy in the manner expected if gravitational waves carry that energy away. More recent systems have extended these tests into regimes involving multiple relativistic effects at once. In carefully timed binaries, the pulse becomes a marker moving through curved spacetime, and every delay or drift can be compared against theoretical prediction. A neutron star orbiting another neutron star, or in some cases orbiting a white dwarf, offers a setting where gravity is strong enough to matter deeply, and the clock is clean enough to register the difference. This is a powerful combination. Most astronomical objects are large enough and messy enough that precise timing of their internal process is difficult. Most laboratory clocks are precise enough, but not embedded in strong gravity. A pulsar occupies both worlds. It is a natural clock placed where relativity matters. That alone would secure its importance. Yet the usefulness of pulsars for gravity reaches further. The pulsar timing arrays now built from networks of stable millisecond pulsars turn the galaxy into part of an observatory. Each timed pulsar becomes a reference point, and together they form a detector for the slow gravitational shifting of spacetime caused by immense systems far beyond the Milky Way. If the emerging evidence for a nanohertz gravitational wave background continues to strengthen, then pulsars will have helped open an entirely new band of the gravitational universe, one too slow for ground-based interferometers and too vast to touch by any other present method. The significance of this is difficult to overstate, though it need not be stated loudly. A rotating remnant no larger than a city can assist in revealing the collective murmur of supermassive black hole binaries across cosmic distances. The smallest and densest known stellar remains help disclose the motions of the largest black holes in the universe. Scale folds inward on itself. The usefulness of pulsars in gravity therefore does not make them feel ordinary. It makes them feel woven into the deep structure of the cosmos in a way few other objects are. Dense matter is another frontier where pulsars continue to matter, precisely because they withhold direct access. The mass and radius of a neutron star depend on how pressure behaves at extraordinary density, and that behavior depends on the still uncertain equation of state of dense nuclear matter. Every improvement in mass measurement, every tighter radius estimate, every gravitational wave constraint on tidal deformability, every cooling observation, and every carefully interpreted glitch helps narrow the allowed possibilities. A heavy neutron star rules out some overly soft descriptions of matter. A compact one may pressure certain stiff descriptions. The way a merged neutron star remnant behaves after collision can hint at what kinds of internal support are available before collapse into a black hole. The curve of temperature decline in a young remnant may suggest neutrino processes or phase changes in the core. None of these measurements reads the center directly. Yet together they form a tightening circle around one of the major open questions in physics. What does matter become when compressed beyond atomic nuclei but not yet swallowed into full gravitational collapse? Pulsars keep this question alive because they embody it rather than merely symbolize it. They are not thought experiments. They are existing objects distributed through the galaxy, carrying the answer in their interiors while revealing only traces of it through their observable behavior. This makes them as frustrating as they are useful. Every improved constraint is a gain and an admission of distance. There are also more practical possibilities, quieter but still remarkable. Pulsars can function as navigation markers. Because their pulses are regular and some are stable over long intervals, spacecraft can in principle use them as natural beacons for autonomous positioning far from Earth. This idea has been tested in concept and, to a limited degree, in practice with X-ray timing approaches. A craft moving through deep space could compare the observed arrival times of pulses from selected pulsars with predicted arrival times at a reference location and infer its own position. The method is demanding and not yet a replacement for existing navigation systems. But the principle remains elegant. A dead star becomes a reference lighthouse not only in metaphor but in actual navigation logic. The galaxy already contains its own timing network, built not by intention, but by collapse and rotation. This possibility carries a kind of calm irony. Objects formed in some of the most violent events known may someday help guide machines through interplanetary or even interstellar space with quiet regularity. The extreme becomes serviceable without becoming less strange. Pulsars also illuminate the interstellar medium, the diffuse gas and plasma that fill the space between stars. As their signals travel across the galaxy, they are dispersed, scattered, and rotated in polarization by the material they cross. Measuring these effects across many pulsars helps map the electron content and magnetic structure of the Milky Way. Here again, the pulsar becomes more than an isolated curiosity. It turns into a probe of the medium surrounding it and surrounding Earth. Some of the most detailed pictures of the galactic magnetic field and electron distribution depend in part on pulsar measurements. The pulse, once corrected to study the star itself, first has to be allowed to reveal what it encounters along the way. It becomes a line through the galaxy, marked by every cloud and field it crosses. This use feels almost modest compared with gravitational waves or dense matter, yet it is part of the broader theme. Pulsars matter because their signals are clean enough to carry extra information. They never speak only of themselves. More speculative possibilities remain at the edge of current research, grounded enough to be taken seriously, uncertain enough to remain open. Some scientists have explored whether pulsar timing might reveal the presence of dark matter if certain compact clumps or fields influence pulsar arrival times or alter neutron star structure in subtle ways. Others have considered whether primordial black holes, if they exist in certain mass ranges, might occasionally interact with neutron stars, perhaps being captured and affecting their evolution from within. These ideas remain unconfirmed and in many cases highly constrained, but they illustrate how pulsars reach beyond ordinary stellar astrophysics. Because they are dense, precise, and long-lived, they become sensitive to phenomena that might scarcely register elsewhere. If the universe contains hidden sectors of matter or rare compact relics from the early cosmos, neutron stars may be among the places where traces of those sectors become visible first. This does not mean such signals have been found in a decisive way. It means the logic is sound enough that pulsars remain part of the search. Their usefulness extends to the border between established astronomy and deeper cosmological speculation. Even without invoking such possibilities, the existing limitations are enough to keep the field open. The number of known pulsars, though large, still represents only a small fraction of the neutron stars thought to exist in the Milky Way. Estimates suggest that the galaxy may contain hundreds of millions of neutron stars, perhaps more, while only a modest share are observed as pulsars. Some are too old and faint. Some never beam toward Earth. Some may be quiet in radio but active in other bands not yet surveyed deeply enough. Some may live in crowded or distant regions where detection is difficult. The visible pulsar population is therefore less like a full census and more like a selected sample shaped by geometry, age, wavelength, and instrument sensitivity. This matters for every broad conclusion. The family portrait, rich as it already is, may still be biased in ways not fully appreciated. Certain paths of neutron star evolution may be underrepresented simply because their observational window is narrow. Some rare categories may prove less rare when better instruments arrive. Others may vanish as separate categories once larger populations reveal smoother continuities. The hidden majority keeps the field unsettled. A new survey can still change the proportions of the known family in meaningful ways. The future observatories likely to transform pulsar science are therefore watched closely. Radio facilities with wider fields of view, greater sensitivity, and stronger computing support will probably uncover many more pulsars, including faint millisecond systems, exotic binaries, and intermittent sources previously missed. The Square Kilometre Array, in particular, is expected to deepen this search dramatically if it reaches its intended capabilities. More stable timing baselines will also strengthen the search for low-frequency gravitational waves and improve tests of relativity. X-ray missions may tighten mass and radius estimates. Continued gravitational wave detections from neutron star mergers will further constrain dense matter. It is tempting to imagine that with enough observation the major questions will simply close. Pulsar history suggests a more subtle outcome. Better observation usually does narrow uncertainty. But it also reveals new behaviours, transitional states, and exceptions. Every clear pattern seems to produce a more refined anomaly beside it. The subject advances not by moving from mystery to completion, but by replacing broad mystery with more disciplined mystery. This is a strength rather than a weakness. Pulsars remain scientifically fertile because they continue to resist oversimplification. Some of the most important unfinished questions sit very close to their identity. What exactly is the interior composition of the most massive neutron stars? At what density, if any, does quark matter appear in nature? How does coherent radio emission arise in detail within the magnetosphere? Why do some pulsars switch states or emit intermittently while others remain steady? How do magnetic fields evolve over long timescales, especially in the transition between ordinary pulsars, high magnetic field objects, and magnetars? What mechanisms govern the full range of glitch behavior? How many neutron stars remain hidden because their beams never cross Earth? And how different might that unseen population be from the one that is known? These are not marginal details. They cut through the heart of what a pulsar is. Even the definition of the class can blur at the edges when transitional systems, central compact objects, and unusual transients are considered. The deeper astronomy reaches, the less final the labels appear. There is also the unresolved emotional geometry of the subject, though it never needs to be stated dramatically. A pulsar is a remnant of death, yet it behaves with precision. It is tiny against stellar scales, yet it influences nebulae, tests gravity, maps the galaxy, and perhaps reveals gravitational waves from distant black hole populations. It is a clock made of catastrophe. It is a laboratory hidden inside a point of light. It is one of the most measurable objects in the sky and one of the least directly accessible. These juxtapositions matter because they explain why pulsars continue to hold attention across so many fields. They are not merely extreme for the sake of extremity. They compress multiple fundamental problems into one observable source: matter under pressure, magnetic structure, relativistic gravity, binary evolution, supernova physics, plasma emission, galactic structure, gravitational wave astronomy, and perhaps traces of darker possibilities all meet in the same class of objects. Few cosmic phenomena offer such a concentrated intersection. Yet even at this point, after decades of measurement and theory, the final picture remains open. The beam that crosses Earth can be described. The star's spin can be timed. The mass can sometimes be weighed. The field can be estimated. The orbit can be mapped. The surrounding nebula can be imaged. The population can be surveyed. But the center remains hidden. The engine of coherent radio emission remains partly unsettled. The full life story of many neutron stars remains incomplete. The hidden population remains large. The future detections remain likely to surprise. In that sense, the pulsar continues to do what it has done since its first discovery. It offers a signal that seems at first impossibly regular, then opens into a structure of layered uncertainty. Data leads to anomaly Anomaly leads to deeper model. Deeper model reveals a new edge of ignorance. The object becomes more useful, more constrained, and more mysterious at the same time. This is not a temporary stage waiting to be outgrown. It may be the enduring nature of the subject. Pulsars stand in the galaxy as rotating remnants that keep time with exceptional fidelity while withholding their deepest matter from direct view. They mark space-time, test theory, guide inference, perhaps guide future craft, and hint at hidden populations and hidden phases of matter. Their beams sweep on whether Earth lies in their path or not. Most do not announce themselves here at all. The known ones blink through the cosmos as if giving evidence in fragments, one pulse at a time, precise enough to trust, incomplete enough to keep the dark around them open. The known pulsars continue their turning whether any observer listens or not. Across the Milky Way, old remnants drift through the dark with beams angled into emptiness, or into regions where no instrument waits. Some move silently by Earth, because their sweep never crosses this world. Some have already faded beyond easy detection. Some are still young enough to light their surrounding nebulae. Some are ancient clocks spun up again by close companions. Some carry magnetic strains so severe that they break into bursts. Some may hold interiors where matter has crossed into form still uncertain in theory. Their differences remain real, but beneath those differences the same quiet fact persists. A star collapses, matter compresses, rotation survives, and something small and severe is left behind to mark time in the dark. That is why pulsars never settle into a single finished image. They are at once remnants and instruments, endings and continuations, precise signals and unresolved objects. Every pulse that reaches Earth carries order from a place built by collapse. Every timing irregularity suggests that the order is negotiated inside the star, not simply given. Every improved measurement narrows some possibilities and leaves the center hidden. In that way, pulsars remain balanced between explanation and distance. They are among the most exact objects known to astronomy, yet they still keep their deepest structure under pressure and out of sight. Far from Earth, a neutron star turns again. Its beam cuts across cold space, passes dust, plasma, and magnetic fields, and for a brief instant reaches a receiver on one small planet. The signal arrives as another clean mark in a long sequence. Behind that mark lies gravity, collapse, heat, magnetism, quantum matter, and a history older than the observation itself. The pulse passes, darkness returns, then the star turns once more, and the mystery resumes its measured rhythm.